You're walking across a concrete slab or a wooden floor, and you feel a slight bounce, a tremor, maybe even a visible sag. Your instinct is to think, is this safe? Deflection. The technical term for this bending or sagging under load is one of the most common and misunderstood behaviors in structures. It's not always a failure, but excessive deflection is a serviceability failure that leads to cracked finishes, misaligned doors, and a real sense of unease for occupants. So why does it happen? It's not just about weight. It's a battle between force and stiffness. And time is a hidden enemy. Let's look at the 5 core reasons slabs give in to gravity. The primary driver is load, but we must separate dead load and live load. Dead load is the permanent weight of the slab itself, plus finishes like tile and partitions. Live load is temporary people, furniture, stored materials. When you add live load, the slab deflects immediately. This is immediate or elastic deflection. When you remove the load, if the slab is properly designed, it should spring back. The amount of this bounce is governed by 2 fundamental material properties: the modulus of elasticity, which is the material's stiffness. Concrete has a high E with a lower one, and the moment of inertia, which is the shape's resistance to bending. This is why the span-to-depth ratio is the golden rule. For a concrete slab, if the span L is too great for its depth E, it will deflect excessively. A pro tip from structural engineers: increasing the depth of a slab increases its moment of inertia by the cube of the increase. Making a slab 20% thicker makes it over 70% stiffer in bending. That's why depth is your most powerful tool against deflection. But here's where it gets critical: long-term deflection, or creep. Concrete is a viscoelastic material. Under a sustained load like its own dead weight and permanent partitions, it continues to slowly deform over years, even decades. This is creep. The steel reinforcement holds the concrete in place, but the concrete itself slowly flows, leading to permanent sag. This is why you see cracks in non-structural walls and gaps under skirting boards years after a building is completed. Creep is magnified by higher stress levels, weaker concrete, and improper curing. A common and devastating drafting mistake is not accounting for creep in the design, or specifying concrete with a low modulus of elasticity. The third major cause is shrinkage deflection. In reinforced concrete slabs, shrinkage isn't always uniform. If the reinforcement is asymmetrical, for example, more rebar at the bottom of a slab than the top, which is typical, the slab will curl as it dries and shrinks. The concrete with less restraint, the top shrinks more than the bottom, causing upward curling at the edges. This then gets compounded by later loads, leading to complex cracking patterns. This is a material behavior issue, not a load issue. Fourth, support conditions are everything. A slab simply supported on 2 edges will deflect much more than a slab fixed at its supports or continuous over multiple spans. Designing for continuity, ensuring the reinforcement can develop negative moment capacity over beams or walls is key to reducing deflection. A slab that appears continuous but isn't detailed for it will crack and deflect at the supports. Finally, construction sequencing and formwork play a huge role. If the supporting shoring and reshoring are removed too early, before the concrete has gained enough strength, the slab will deflect under its own weight more than designed. If the formwork itself sags during the pour, you build that defect right into the structure. In essence, deflection is a guarantee. The goal of engineering is to predict and control it, ensuring it stays within acceptable limits. Often L360 for live load, meaning a 30-foot span shouldn't deflect more than 1 inch under live load to prevent damage to finishes and the human perception of bounce.